In this question, we're thinking about whether or not our kitchen scales are actually correctly estimating the weight that they're reading off, right? And so what we're doing is we're taking a weight that we know weighs exactly 150 grams, and we have 50 different kitchen scales, and we're weighing this 150-gram weight on all of these different kitchen scales. Now, of these 50, 29 were too light, 21 were too heavy. And so what we're asking is it the case that more than half of the kitchen scales underestimate the weight, right? So, where are we actually at with this? Well, the interesting component here is that we're dealing with a binomial population, right? And so if we think about each of these kitchen scales as being a binomial experiment with sort of equal proportion, then what we could say is that the underlying distribution that we're working in here is going to be a binomial where our n equals 50, and we have some unknown proportion, and that proportion is what we actually want to do inference about, right? Now, if we think about the observed proportion, and we think about which of them are going to be too light versus too heavy, right? We have 21 out of the 50 are going to be too heavy. The remaining 29 out of the 50 are going to be too light, right? And we have to decide which of these we want to actually consider to be the event of interest here. The interesting component that we're thinking about is just that we want to know whether more than half of this kitchen scales are underestimating the weight, right? And so it's sort of easier for us to think about the proportion p representing the probability that the weight is actually going to be underestimated, right? And so if p is going to correspond to probability of underestimation, then what we have is that p hat is going to equal 29 out of 50, right? Just the proportion that we're actually observing in the sample. Now, if we're actually thinking about what is the null hypothesis, well, the null hypothesis is going to be that the true proportion is going to be p is less than or equal to 0.5. And why is that? Well, we want to know, do more than half of the scales underestimate the weight, right? And so if we want to see is there evidence in favor of that conclusion, we need to make our null hypothesis that less than or equal to half of them are going to be, right? So sort of put differently, we take our null hypothesis to be that the probability p is less than or equal to 0.5. H1 is going to be that p is greater than 0.5, and we're asking, do the data support this conclusion, right? Now, we're in a situation here where we can think about our test statistic, right? And our test statistic for the binomial population is going to be very similar to the one that we're using in the normal population, right? And that's because we can say that the binomial is going to be approximately distributed as though it's normally distributed, right? And so here the question is n equals 50 sort of enough in our samples for this approximation? Generally speaking, what you want to consider is what's n times p and what's n times 1 minus p. And in our case, p is going to be 0.5, right? And so then you're thinking about 50 times by 0.5, which is going to be 25, or 50 times by 1 minus 0.5, which is still 25, right? And we've said that as a general rule of thumb, as long as these two values are greater than or equal to 10, you're probably okay. And so in our case, we're probably okay to use the normally distributed approximation, right? And so then in that case, what we do is we take p hat minus p naught divided by the standard error, right? Which, if the null hypothesis were true, is going to be p naught times 1 minus p naught divided by the square root, or we're already sort of square rooting here, sorry, divided by n, right? And so we can actually just fill in our values here. We get our 29 over 50 minus 0.5 0.5, not 0.05, divided by square root of 0.5 times by 0.5 is going to be 0.5 divided by the square root of n. Right? And in this case, the square root of n is the square root of 50. Just as we're getting used to doing, we can plug this into a calculator and actually read off some observed value, which in this case is going to be 1.131, right? And at this point, what we'll say is that if the null hypothesis is true, then this statistic should follow approximately a normal 0, 1, right? And so drawing this out, as we are apt to do, we put in our approximate bell curve shape here, and we're observing something that's going to be, say 1.131, right? And so the question is, what's the probability that, assuming that the null hypothesis is true, we observe something that is at least as extreme as this, right? And in our case, we're testing this one-sided hypothesis, right? And so the only thing that's going to be more extreme is if we are up into the tail of the distribution here. And so in other words, we want this tail probability, right? So a bunch of ways that we can write this out. Remember that this is the normal CDF. And so ultimately what that means is that the p-value is going to be 1 minus the normal CDF, which we'd express as phi, at 1.131. As always, we don't actually have to work out any of this by hand. We're going to rely on software or critical values. And if you do that, what we should find is that this value here is going to be 0.871, say. So this will be 1 minus 0.871. And so then we can work out that our p-value is going to be 0.129. Right? And so now here we have to decide what's the alpha that's going to be reasonable. But most of the time we're thinking about taking alpha to be less than, say, 0.1. Right? That's sort of the highest alpha that we're considering. And so sort of no matter what, we're thinking here that this p-value is going to be too large to conclude that this is going to be significantly different. Right? The other thing that we'll point out here is that if we had allowed the difference to go in either direction, right, then we'd also include this negative 1.131 down here. We'd include the secondary probability here, and our p-value would be twice as high, right? And so, again, this is an indication of why we might want to try to avoid using these types of hypotheses here. But ultimately, there's not very strong evidence in these data that we have sort of a significantly different proportion of them beyond just the 0.5, right? And of course, 0.5 sort of suggests that you're going to have some that weigh too heavy, some that weigh too light, and ultimately they'll sort of balance each other out, right? So there's not very strong evidence here. We're going to fail to reject the null hypothesis for any reasonable value of alpha, and we'll just operate as though half of scales are going to underestimate the weight, half of them are going to overestimate the weight.